Hello. In the previous video, we looked at the process of an enzyme and substrate coming together to make the complex, eventually catalyzing the reaction and releasing the product. And we started to look at reaction coordinate diagrams to see how delta G is changed when you go from a reaction that's not catalyzed to one where it is catalyzed with an enzyme. In this video, we are more concerned about this delta G naught double dagger and how to lower it using the enzyme. We're going to look at the proximity model, and we are going to understand the mantra enzymes bind transition states best. I want to start with knowing how to lower delta G double dagger. Don't forget that the double dagger refers to the difference in delta G from the valley to the transition state. This is the double dagger. And so when we have an enzyme that lowers the delta G, it actually lowers the enzyme substrate complex as well. So we measure, in this case, the new delta G is from this starting point right here. This was all shown in the last video. Whereas the delta G in this case, for the non-catalyzed reaction, starts right there. Let me give us three situations where we are looking at the rate and how this can be lowered. Let me describe three situations, and we are going to look at the kinetics and thermodynamics of these three. The first one is uncatalyzed bimolecular reactions. You recall that therefore your rate expression would be rate equals K times the concentrations of the two reactants. So this is uncatalyzed, so your reactants are fairly free, and you will need to combine them into somewhat of a single restricted transition state. The conclusion here is that this is entropically unfavorable. Right, going from two molecules to one. Now take a look at this situation where it's unimolecular. We'll go from one molecule to one transition state. But the thing is, that reactant, before it reaches the transition state, is fairly flexible. And then it gets rigidified into a transition state which is about to undergo a reaction. Don't forget, the transition state is a high energy transient species in the reaction coordinate diagram. This also is entropically unfavorable. Here the rate law is just concentration of one molecule, and again, entropically unfavorable. Now let's go to the catalyzed reaction using an enzyme. The enzyme uses the binding energy of substrates, the binding energy when the substrate binds the enzyme, to organize the reactants to a fairly rigid enzyme-substrate complex. What I want us to remember is that much of the entropy cost in rigidifying this complex is paid during the binding. And we got to remind ourselves on the reaction coordinate diagram, see how the enzyme substrate complex is actually lower in energy. That is due to the energy of binding. Now, we could say a couple things about the thermodynamic parameters at this point. We could say that, in this process, the delta S is unfavorable. That's negative. We lower the entropy because we get more rigid. But the thing is, the delta H is very favorable. That's the binding. And if delta H of the binding is favorable, then the delta G of the binding is favorable as well, if this delta S is not too bad. And again, we are saying that much of the entropy cost is paid during this binding. Other thermodynamic equations we could have. We could think about maybe the entropy of the transition state while it's catalyzed is much higher, much more favorable than the entropy of the transition state transition when you're not catalyzed. And therefore, you could think of delta G of the catalyzed process to be much lower, much more favorable. Next, I'm going to talk about the idea that when we have an enzyme bringing molecules together, that can lower the delta G due to what's called the proximity model. Let me use a model reaction to talk about this idea of proximity model, and we're going to look at the rate of anhydride formation and how it shows a strong dependence on the proximity of the two reactive groups. This is our first situation where we have the two reactive groups that are untethered. They come together, you kick out an alkoxide, and we get a base rate. Let me draw two other situations where we make an anhydride, and we're going to compare those rates to this first rate. Now let's consider the next two situations. For letter B, we tethered the two reactive groups, and by making them exist close to each other, we can increase the rate. So we can find the relative rate of rate B compared to rate A by doing this ratio, and we find that rate B is 10 to the 5 times faster, this is in molarity, faster than our base case A. Now the thing is, why doing something like this increases the rate even more? Because we already tethered in part B. What's going on with part C? Well, if you think about part B, you still have rotational freedom quite a bit. That single bond, this single bond, this single bond. What C is doing is that it's restricting the rate, or it's restricting the rotation of some of these bonds. We still have some rotation here, okay? But not only is it tethered, but also we can't get any full rotation on this bond. Okay, so, by rotating this bond, we could get these two groups pretty far apart still. Not in this case. So here we restricted the motion even further. Can you imagine an enzyme being able to do that? Being able to get two reactive groups together, close in proximity, but also restrict their movement so that the reaction happens a lot faster. The next thing I want to talk about is this idea that really the enzyme, for it to work really, really well, it doesn't really want to mimic, it doesn't really want to bond the substrate that strongly. It wants to bind the transition state more strongly. What we want to remember when we think about enzyme lowering the delta G double dagger is that enzymes bind transition states best. Let me jot down a couple notes to try to illustrate this. Here I have 3 key points that were proposed by Linus Pauling in 1946. The first thing is that enzyme active sites are complementary to the transition state of the reaction, which means that the enzyme bind transition states much better than substrates. So the binding of the substrate is kind of loose, not really perfect, but as the substrate transitions or goes to the transition state on its way to the product, that's when the really strong binding and the shape matching really occurs with the enzyme and the transition state. Because in the transition state, we will find stronger and additional non-covalent interactions with that transition state, which lowers the activation barrier, which is the delta G, not double dagger. So this idea that once the substrate gets into its transition state, we get even stronger and more non-covalent interactions, that makes the delta H of the catalyzed reaction much more negative than the non-catalyzed. And therefore, if that's true, then delta G also is going to be much more negative than the non-catalyzed reaction. I have one more figure that will help summarize what we just said here. Let's summarize the entropic and enthalpic factors in catalysis. In this case, we are making a covalent bond. We're combining two reactants. And here's the catalyst, and you can see that when we bind the substrates with the enzyme or the catalyst, it's not a perfect fit. But as the two reactants start to combine and go towards the product, we get to what's called the transition state. Here, the proximity and the orientation that the enzyme puts these two reactants in, they favor the formation of the transition state. And what that results in is that the delta S of the transition state, when it's catalyzed, is much greater than the delta S of the transition state when it's not catalyzed. Secondly, because the enzyme binds the transition state stronger than the actual substrates, we have a good match, and what that does is we add a lot of strong non-covalent interactions between the transition state and the enzyme. What that does, it makes the delta H in the catalyzed process much more favorable and negative than in the non-catalyzed process. Ultimately, what happens is once this reaction occurs, we get out of the transition state and we get into the enzyme product complex that we see over here. And then it's just a little jump to release the enzyme and the product.